And so we're going to start one more application. We got maybe two more applications of the derivative. On Friday, Eddie, are you going to be here on Friday? Or do you have games? You'll be here, cool. Nobody has games on Friday, this Friday? No, cool. We're going to do it in class. I'm going to give you a problem. It's kind of like nice to not have web work all the time, right? I mean, web work gets a little tiring. I mean, I'll make you web work if you want it, if you guys want it. Sophia looks like she really wants web work. Is that true, Sophia? At least you can work on it till you get it right, but sometimes that's also why it's horrible. So on Friday, we'll do an in-class problem set. It'll be smaller than the one before break. That was pretty heavy. It was pretty intense. So we'll do problem in-class problems, and that'll just be like a work day. I'll make up some stuff. We'll work together. We can talk. All those things. Otherwise, we are starting what's called optimization. That's a nice pen. That looks good. It's good stuff. Good stuff to come back, have a nice pen, shit's aligning, we are rolling. So optimization, we have a problem like this. Find the max, min, values of some function, f of x. Now you could get a picture and you could estimate them, and but anybody can do that. Anybody can make a picture and look at it. We're going to use the calculus we've learned to really find these things and to prove that it's not just what it looks like in the picture. So we're going to do two versions of this. First, this is today. We're going to do what's called unconstrained optimization. And that means there's no restrictions on the input. And then, since Friday's going to be a work day doing this stuff, next Monday, we will do what's called constrained optimization. So this problem right here is essentially this guy right here. Just find the max mins. Constrained optimization is find the max min values of f of x. So same start to the problem, but we have x being constrained on a closed interval. So x is between two values. This turns out to be a lot easier. This is actually, we got a nice plan for this. You'll like it. This is where we're going to have to do some more intense work. So let's look at a graph. Yeah, I'll keep using this color. Let's get an example out here. I got a picture, and you'll probably want to make it kind of as close as you can to what I'm doing as you can. Okay, that's pretty weird. That's a weirdie. Good colors. Black will be nice with that. So this is a graph of f of x. You can look at this graph and you can see there's some places that are higher than others, places where it's low. So let's go through and talk about some terminology here. So let's also give some coordinates. Let's say that this is A, this is B, this is C, this little crease is D, and then this top of this hump, so you got to estimate, where do you think the top of that is? I'm not doing a great job. We'll call that E. That looks pretty bad. Your mileage hopefully is better. I'm drawing fine. So we got this graph. And when I go through here, just from left to right, I notice that as I approach x equals a, I'm moving up on the left side, and then I'm going down on the right side. So notice here we go up and then down, and I can go to this peak right here, and I can say, oh, that's kind of a local hill. So we call a local maximum. It's a local maximum because nearby, in a local area, near it, it is the highest point. So highest point in a small interval around x equals a. Trying to spell. I'm going to try. I got a new thing. I made a resolution just now. I'm going to try to spell better. That says around x equals a. What do you think this point's called?
Local.
That's a local minimum. It's not the most minimum thing. It's not the lowest point on the whole graph, but in a region near B, it is a local minimum. So here we have a local. It is nearby the lowest point. C, what do you think? Wait, you said something a little different, didn't you? Did you say? Oh, shit, she called that an absolute maximum. It is the highest point nearby, so it's also a local maximum here, because nearby it's the highest point, but out of everything in consideration, this guy right here is a global or absolute maximum. It's also, you might want to note here, it's also a local maximum. And then we got this guy here, here's a local min. So let's label that little min. And then here's a local max. Cool. Is this function differentiable everywhere? No. No, why do you say that, Ed? There's cusps. Is that what you're going to say, Leo? Yeah. So you've got these sharp points. So the function's not differentiable here, it's not differentiable here, and it's not differentiable here. That little, like, I guess in my brain I keep thinking little butt crack area, and you might be thinking that too, I don't know, but it's just like 12 years old, never grew up. That is not differentiable because it's sharp. So the derivative, so f prime of A, f prime of B, f prime of D do not exist. And you might want to put here the nice word cusp. Cusps. Sharp points. What is the value of the derivative here at that highest point? What's the value, what's the slope of the tangent line right at the top? 0. So at this local max, I've got f prime is 0. Also here, f prime is 0. We don't have any low spots where f prime is 0. It seems like those are the only two. So we have f prime of C is equal to f prime of E, and those are both 0. Notice that we have two things happening at every local max or min. So if you have a local max or min, you're either coming to a peak or you're coming to a rounded peak or a rounded trough. So when we have, if you have a local max or a local min, the derivative is undefined or 0 at those points. So we're going to use a definition because this is how we're going to hunt for these guys. These are the clues we're going to look for. So a point, x equals c, is called a critical number, that's what our book calls them, but it could also be value. That's a common way to say it. I'll probably call it critical value because that's how I learned. If f prime of c does not exist, or f prime of c equals 0. I want to point something out with a picture that just because these things are happening does not mean it's a max or a min. So we have to be careful. I wanted you to pay attention to this flow here. So critical value, or max or a min, implies critical value at that point. At that X location. It doesn't go the other way, but not every critical value gives a max or a min. And the picture that I can do for this is real simple. This is the example you want to keep in mind. X cubed. That's the perfect example to see that this is the case. So let's take a look at a better marker. It's not nice to give that to someone else. Example. F of x is x cubed. We got a picture, hopefully you got a picture in your head of this serpentine graph. Like so. Like so. Looks like that, you know, good old cubic. Could be better. This is a little broken, my horizontal axis. Use your imagination. So this is x cubed. And we know that f prime of x, we got this down, that's 3x squared. Where is that equal to 0? So if I set this equal to 0, what do I get for x? What's the solution? 0. 0. 0. Everybody good with that? That the only solution to this equation is x equals 0? Yeah. So the solution is x equals 0. And that means that x equals 0 is a critical value for f of x. Is it local max, local min? Minimum. Doesn't look like it, right? You come up on this, so we're increasing on this side, but we just keep on increasing, right? You come up, you're going up, you hit 0. As you move to the other side, you just keep going up. In fact, let me prove this to you. Look at this first derivative. Notice that, and this is a good way into our first test, that f prime of x is greater than 0. It's positive because x squared is always positive if x isn't 0. So this thing is always positive, and that means f is increasing. Everywhere except for a moment right at x equals 0. Everywhere except at x equals 0, which is just a moment. It's just a momentary pause before you keep on cruising upward. What does the derivative look like at a max or min? So let's think about that. So contrast that. Let's go on to this board over here. Oh, it's such a pretty graph, but whatever. Oh, good. Here's my pen. All righty, friends, so let's clear it up. What if I have this picture right here? And let's call that x equals c. Right at the point, this is f of x. Just look at the cases. Just some simple cases. So what's happening on the left of this critical value? We know that f prime of c equals 0. What's f prime of x when x is less than c? So to the left here, what's the value of the derivative? Positive, negative, 0? positive because we're moving up, right? So on this left side, looking at the tangent lines, remember derivative is tangent slope, is instantaneous rate of change. You see that tangent slope is always positive. So you could put over here, slope is positive. And then, Sophia, what about on the right? It's negative, and then it becomes negative. So, I trace it properly. So here, the slope is negative. And that's always going to happen when we have a maximum. You're going to go up on the left side and down on the right side. And so that f prime of x is, let's see, is positive when x is less than c. It's negative when x is greater than c. And we have a maximum there. So this is actually part of what's called the first derivative test. What we do, the plan is this. And the plan is step 1, find all critical values. Step 2 is mark these on a number line. Three, test the sign, S-I-G-N, no trig. Well, not for this problem anyway, not for what I'm writing. You'll see some trig. Test the sign of f prime of x in between and left and right also, right sides, of all critical values. And let's look at what that would look like if I have a max. So let's actually write this out. If the sign of f prime changes as we move from left to right across a critical value, just like here, where it moved from plus to minus, if the sign of f prime changes as we move across a critical value, we have a maximum, a local maximum at x equals at the critical value. Let's just say that. Local max at the critical value. What's going to happen if I have a minimum? How is this going to change if I have instead this, and here's x equals c right here. Derivative is what on the left? Negative. We're moving down, and then it becomes positive. So that sign change tells you you've got a local max or min. You just got to look at the direction of the change, the order of the change. If sign, if sign is plus on the left and negative on the right, just like that picture, we have a local max. Sorry, this shouldn't say local max, or it should say local max, but it should say or min. Just add that in there. And now I'm doing specifics of which is which. Local max, if we move from plus to minus on the derivative. If sign is negative on the left and positive on the right, that means you're moving down and then up. We have a local min. If the sign doesn't change, then we have neither. Then no extreme value. I'm going to toss that word in here. No extreme value. This is called the first derivative test. And we're going to practice it next. So this whole thing right here, step 4, and kind of this whole plan, this is, sorry Sam, I know that came flying at you. You probably could catch that shit. Pretty good. Yeah, hopefully, right? Yeah. This, This is called the first derivative test. So let's practice. Got a good example. Set up here. All right. And I'm gonna kind of like field us some cred, and we're not gonna have to find the derivatives. I'm gonna give you the derivatives, and then we're gonna think about them. So no derivatives need to be taken. Don't do, I know I said once, first thing you should always do is take the derivative. I did that. So don't differentiate. Example. Suppose g prime of x, so got the first derivative, is equal to, is this the guy I want? Yeah, I guess this is the first. Oh, yeah, good, I got a better one. E to the negative 2x times 3 minus x times x plus 1 quantity squared. I'm gonna slow down a little bit. I've just been going like a maniac. Got all my energy back after the break. See if I can blow it all today. Okay, let's go through the plan. Your turn. 1, find the critical values. And before we get too deep into this, is there any x value where that's not defined? So that we have like division by 0 or something like that. There's no division, right? So we don't, I guess this could be a division. Why can't this cause any troubles for us? What do we know about that? What's the graph look like?
It's never 0.
What's that?
It's never 0.
Never 0, exactly. It's always positive. So a good thing to keep in mind is that note, e to anything is always positive. It can't give you a 0. It can't produce critical values. So it's kind of a trick, right? This is irrelevant. This can't give us critical values. But we have a product of things. So I have something times and, something times something else equals 0. I have a product. And the way this works, the only way a product can be 0 is if one of the pieces is 0. So getting that thing factored up there, this means this equals 0, or this equals 0, or this equals 0. And you know, if there's more pieces in there, then there's more of these possible things that can be 0. So when I come to this guy, I could have a 0. So I'm going to set g prime of x equal to 0. And that would mean that this whole thing, let's write it all out, 3 minus x plus 1 squared equals 0. So I already know this can't be 0, thanks to Joshua. This could be 0. What would x need to be for this to be 0? 3. Everybody good on that? So that's a solution. Then what about here?
-1.
-1, thank you. So x equals -1. So here are my, oh my God, I don't know what that shape is. That's a critical value. Critical values. Got 2 of them, 3 and -1. Let me stop. Let me know if this is cool. All right, if that's cool, then copy this. Oh, that's a nice one. Make a number line. So I'm going to go to step 2, mark on the number line these points. So I've got -1 and 3. You don't need to get too crazy with your number line. Just put the points on in the right order. Don't worry about scale, it's all good. It doesn't matter if your scale's appropriate here or not. So these are my critical values. I'm gonna put a little dot there. Notice that that gives me 3 regions to test. Left, middle, right side. So what I'm gonna do is pick a value out of each one of these, put it in the first derivative, and see if it's positive or negative. So let's write that out over here. Okie dokie. So, let's see, what am I gonna do? So we'll test a value from each region. And when I say test, I mean plug it into the first derivative. So test means plug into f prime. And don't get crazy here again, like keep this simple and I'll show you what I mean. I don't even care what specific values come out. I don't care if this is 7 or 7,000 that comes out. All I care is if it's positive or negative. So let's call this region 1, let's call this region 2, and region 3, just so I can notate over here. What do you want to plug? Give me some point in region 1. -2, like it, let's do it. So in region 1, use x equals -2, pick your favorite. So I'm gonna look at f prime of -2. Now watch how I'm gonna write this. I've got a positive, because that's the E thing. That's always positive, that's cool. What is 3 minus a negative number? That is a positive number. So do you see how I'm getting that? Make sure you see that right here when I put x is -1, I've got 4. But I didn't really even care what the value was. It was 3 minus a negative, it was 3 plus something. So I have positive times positive. And then what do I get when I put -2 into that last little piece? I get a positive because I'm squaring it. Doesn't even matter what I put in there. This will always be positive except when x is -1. And that's one of the critical values. That's where we're at right now. So this thing is positive. And so that means this whole thing is positive. And that's what I'm gonna mark over here. So this was step 3. Here I'm gonna mark f prime is positive in this region. Can you finish up, please? Test the point out of 2, test the point out of 3. Don't multiply that derivative out, you're gonna hate life. Do not do that. Sam, don't do that. That sounds like a Sam move, maybe, to multiply that guy out. Don't do that. Keep it factored. I mean, it's only because you like to do stuff and get things, you know. You're a computational man.
Very much so.
Compute less.
Very much
I know, I know. Use cool Roman numerals. What's the sweetest value in region 2? 0. Always go for the low-hanging fruits. 0. If 0 is something you can use, grab that 0. If you didn't grab, anybody not grab 0 in here because they're like hardcore? Joshua maybe. No, okay, all right. So, okay. Okay, all right, so we're gonna use x equals 0. So we've got f prime of 0 equals positive because it's e to something. 3 minus 0, positive. And that last piece is always positive. Oh shit, does this look right? It's positive. So in this region, f prime is positive. Now before we get to region 3, just think about what we know so far. Increasing, increasing. Then we hit this critical value, so it kind of like just chills out a little bit, but then it keeps increasing. This is like x cubed. What's happening here? increasing, and still increasing. In fact, underneath, let's put f is increasing, so I'm going to translate that into a visual idea. F is increasing here, so this is not a max or a min. Because you have to go up and then down, or down and then up. So I already know that. This probably looks something like this here. Think of that x cubed shape. Something like that. There's possibly some other details. The curvature might not be exactly that. And then what do we got over here? I'm going to grab 10,000. I like x is 10,000. So I'm going to use x equals 10,000. And I've got f prime of 10,000 equals a positive because it's e. 3 minus a big freaking number. Negative? Negative. Something squared. Who cares? Positive. Finally, we've got that thing is less than 0. And the only place it could change sign is at these critical values. So if I know it's positive somewhere in there, it's always positive in there. So here we have f prime is, or sorry, negative. That's what I meant. So f is decreasing here. And that must mean that the graph goes up and then down. Increasing, decreasing. So I have a local max at x equals 3. So since f prime is positive on the left, let's write this out. If you need this, you can look at it later, is on the left side of x equals 3, and f prime is negative on the right side by the first derivative test. We have, and I'm gonna add a little bit extra here. We have a local, and I always have to kind of do this in my head. Here's f prime positive, here's f prime negative. A local max at x equals 3. And here's also, you want to report what is the x value or the input that gives you that, and what is the height, what is the actual output value at x equals 3 of, and so the of is f of 3. I'm going to plug this in, so that's equal to e to the negative 6 times 0. Oh yeah, it's just a good old 0. Cool. Oh wait, shit. No. This isn't the original f. I don't know the original f. Sorry. Oops. Excuse me. Yeah, let's put this here. If we had the original f, that's the derivative. I got myself confused for a minute. If we had the original f of x formula, we'd find f of 3 to know the actual height of that maximum. Sound okay? Cool. Your turn. I'm gonna give you one now. All yours. Unless is there any questions? We can make sure. Everybody good? It's pretty chill, right? Especially when you get the derivative. It's not even calc class in some ways if I take the derivative for you. So let's say, suppose f of x is x plus 4 over x minus 2 divided by x squared plus 1. Of course, you get the quotient. Do not take the derivative. That is the derivative. Sorry. That is the derivative. It's okay. I've got to look up. Sorry. That's your derivative. Find your critical values. When is a fraction equal to 0? When the top is 0. So there's some trickiness going on. This can only equal 0 when the top is 0. When when the top equals 0. And a fraction is undefined when? When the bottom is 0. So just focus on the top, focus on the bottom. That's how you get your critical values. Does that make sense? Yeah, okay, cool. And it was a little tricky. I'm not going to say how yet. You might see it. You see it, yeah? Find those critical values, make the number line, test. Sanity check for you, you'll have 3 regions again. Good. Sounds good to me. Thanks. Sanity check, -4 and 2 are your critical values. Why am I not worried about the bottom? It can never be 0. In fact, what is the least value the bottom could be? What's the smallest? 1 when x is 0. So notice that this bottom part is always greater than or equal to 1. Because you square that x and you add it on. It's 1 plus a positive number, or 0 at the least. So this we can't get a critical value from that. This is the only place we can get them from. And you can also use the fact that the bottom is always positive when you test the sign. It can't screw you up sign-wise, no matter what x value you pick. I'm grabbing -5. 5 is negative times a negative over positive. Notice I'm not even using numbers. I'm only concerned about pluses and minuses. So don't get hung up on computing specific, exact values in these problems. It's not going to help you, really. Oh gosh, low-hanging fruit in the middle. Interesting, maybe. How are we feeling about this so far? Asha, are you feeling okay about that? Okay, cool. So Everybody cool on plus, minus, plus. Awesome. So I can literally make a fake graph underneath here. Up, down, up. That's not the graph. The graph's prettier because we know the derivative's defined everywhere. I can look at that and see it. But it's essentially this, you know, in just a minute, we're gonna actually make this prettier and subtler, but that's all I need right now. I have a local max here, so I get a local max at x equals -4, and a local min at x equals, what was it, 2. Good? Chill. Questions? All right, cool. So, we haven't used second derivative yet, and that's what we're about to. The second derivative test. Let's actually see if we can kind of grok this thing on our own, just looking at a picture. So let's make a fake graph. Got a local max, got a local min. Let's see what's happening. First off, here's my critical values. Yeah. Here I've got f prime equals 0 here and f prime equals 0 here. Just kind of going back to the first derivative test. F prime is positive here. F prime is negative in the middle. And then f prime is positive over here. So just really simple. I already knew that I had a max and a min. I'm not gaining any new info, just kind of thinking about it backwards. The second derivative is the change in the first derivative. So just remember that f double prime equals the derivative of f prime. And we can think of it the same way. So f double prime is positive when f prime is increasing. Getting a lot of derivatives in here. What does f prime increasing means? This means, i.e., tangent slope is increasing. Is that all making sense? So when the tangent slope is increasing, what does that look like? Well, here's a slope, then I move to the right, it goes up. Tangent slope is increasing as I move this way. That is a concave up shape. So notice that this is concave up inside here as that tangent slope increases. And in this over here too, we could have had it, it's like super negative becoming less negative, less negative, less negative, less negative. Oh shit, it's 0 for a second, then it becomes positive, So this is what it looks like when f double prime, the second derivative, is positive when you look like this. When you look like a what? Local what? Local min. So when f double prime is positive, we get a local min at the critical value. So I'm going to look at second derivative. If it's positive at a critical value, it must look like this there, and we have a local min. So remember that this is when f double prime is positive. If f double prime is negative, that means that f prime is decreasing. F prime decreasing looks like this. Super positive slope, move to the right, less positive. Less positive, oh shit, 0 becoming negative, blah, blah, blah. So here you see your tangent slope becoming from positive to more negative, and we get a local max at that case. So f prime less than 0 implies a local maximum. And then there's one other thing that can happen that we're gonna see. We might see something like this. Notice here how f prime is always increasing, or wait, no, it's decreasing. So it's like decreasing here and then increasing here. So here it's always decreasing, here it's always increasing. If it's increasing, decreasing, then increasing. So here f prime is decreasing on this side, f prime is increasing on this side. Or we look like this, where the tangent slope is decreasing and then, wait, that's increasing, right? Because that's negative becoming, so here we have f prime increasing, and then on this side we have f prime decreasing, tangent slope getting more negative. What curve does that look like? We've seen it today. That's the x cubed curve. That's the x cubed. So think x cubed right here when you think of this. This is the flip of this. This would be like negative x cubed here. But what we have is a thing that looks concave down on the left and then concave up on the right, or vice versa. Here we have a point of inflection. So a point of inflection is any place where f double prime changes sign. So let's get at this. Let's get a nice example and work it through. I'm going to show you how to use the second derivative test. So it's same process. Find critical values. That's always our first step. Let me see if I've got better notes to myself on this than what I'm thinking here. Yeah, so the second derivative test.
It should be the exact same thing, just using the second derivative instead of the first.
Yes.
Okay.
Yeah, essentially, yeah, but there's a little subtlety that comes in with it, but it's about the same thing.
Okay.
Yeah, absolutely. So step one is find your critical values. Find your critical values. 2, if f prime of a critical value equals 0, we need this first. So these are critical values, right? This could be, it really needs to be, it could be, or I'll say this, f prime cb is undefined. I guess that's actually the definition of critical value. How about we say so? There we go. 3, if f double prime of that critical value is positive, that means you've got an increasing first derivative and you've got a minimum, local min. If f double prime of that critical value is negative, the local max. If f double prime of the critical value equals 0, we have a possible point of inflection. And if this is the case, we want to know what the sign of f prime is on either side. So a point of inflection, if f double prime changes sign as we move across the critical value. And there we go. So let's do it. Let's start from the very beginning. I'm going to give us the original function. We're going to do the derivatives. We're going to find the first 2 derivatives. And it's a polynomial, so no stress. Low mental activity. So example. Let's say f of x is 3/5 x to the 5th minus 3x cubed. We'll just leave it at that. Let's find the first two derivatives. And then we'll go through this guy together. I mean, everybody could do this and much harder on the exam, so I'm pretty sure we're good to go on power rule and stuff. I've seen what you can do, you can do that. So step one, if I'm using the second derivative test, is get these guys, get these first two derivatives. And then I'm gonna find my critical values. Could you do that, please? Notice I don't have a fraction, so it won't be undefined. I'm gonna set f prime equal to 0 and solve. And here's where your algebra skills will be handy. It's not a clean answer, I'll tell you that. Just right off the bat, expect the answer's not an integer. Well, one of them is. You got one integer. You got 3 solutions. Somebody who's already worked on this, can you help me? What is the move? Leo, what did you do to solve this?
I took out a 3x to the 3x squared.
Like it. Good. Factored out the largest common thing between these two, and then you're left with x squared minus 3. Cool, like that. What's next? Sam?
I took x squared minus 3 and set it equal to 0.
Oh, cool, yeah. So this equals 0 or this equals 0, right?
Yeah.
So you kept this guy, and that's totally cool. So notice here we get right off the bat x equals 0 is 1. Or, and I liked what Sam did. He made this a separate problem, this.
Yeah. And then I solved from there and I got plus or minus.
Indeed. And we get plus or minus root 3. So you could actually factor this thing. And sometimes that can help. Let's just talk about it. We know that we can solve this by moving the 3 over here and taking the square root with the plus minus. So we could easily get that. Or we could factor this. Because this is the difference of 2 squares, it just doesn't look like the squares you wish it was. The thing that's squared, here I have x squared, but the thing here that's squared is the square root of 3. Square root of 3 squared is 3. So this is x minus root 3 and x plus root 3. So if I wanted, I could come and take this thing and do a full factorization. Nothing wrong with that. You get the same info. But having this, well, actually, I guess it'll probably be okay. We might want to test the sign on this. I think it'll probably be okay in that form. Yeah, it'll be fine. It'll be okay. Any questions on getting those critical values? No? Okay. Cool. So we've got our critical values. Now, step 2 is we're going to plug those in to the second derivative. So evaluate f double prime at each CV. So we've got f double prime of, let's do the low hanging fruit, right? Like this one's sweet. What do I get here for 0? 0. Ooh, might be a point of inflection. Definitely not a max or min that I can tell right now. I don't know exactly what this guy is. It actually could be a max or a min too. It just might be deep inside there. So this is needs more examination. Don't really know what that means. But if I do f double prime of the square root of 3, well, let's see, what is that going to look like? So we've got 12 square root of 3 cubed minus 18 square root of 3. You'd probably get your calculator out for this, I'm assuming. That might even be what you just did. Is it? Did you get were you taking the, no, okay, no, okay, you were doing something, okay, you were doing something else, okay, all right, let's see, I gotcha. So this guy here would be nice with a calculator, but we don't have to do that. I'm gonna show you how to do it without that. This is 12 times square root of 3 squared times square root of 3 minus 18 root 3. And I did that because then that's just a perfect 3. And I've got 36 root 3 minus 18 root 3, and holy smokes, that's just 18 root 3s. 36 of them minus 18 of them gives you 18 of them. All that matters is that's positive. I didn't really care if what the actual value was. It's positive, so I have a local min here. So a local min, because I'm concave up, at x equals square root of 3. And now let's do the negative. And we're gonna really make this fancy. We're gonna make 2 number lines. We're gonna make a beautiful graph out of this thing. What's that, Sam?
No, it's negative.
Oh yeah, what does happen? Yeah, if I put a negative in there, what does it do to it? It becomes negative, right? And you see, check that out. If I put a negative on here, I cube it, it becomes negative. And here it becomes negative as well. So it literally just changes the sign, S-I-G-N, of the second derivative. So f prime of negative root 3 is less than 0. And that is a local max. Local max at x equals negative root 3. All right, now we're gonna get it. So we kind of know something like this is happening. Right now, what I've got is this. Let's see, here's root 3, that's like 1.7. Here's 0, here's negative root 3. And not worrying about any particular points. Although, what is f of 0? It's just 0, right? F of 0 is just 0. So I do know that 0, 0 is on the graph, which kind of helps. So I've got a local max here and a local min here. It kind of must look something like this. And I'm going to get in deeper and see what happens. Do you see how I'm getting that picture? So let's actually make 2 number lines and see if we can make that subtle, because man, this was my first turn calc. I was so stoked about this. I was just like making graphs. I was really into graphing. I hope you can find joy in graphing, because it's really cool to not use your calculator. And when the power grid shuts down after a Russian attack one day and we have to graph, we're ready. Thanks, calculus. All right, that's enough of that. When JD's scouring the internet looking at YouTube videos, you'll see that and come get me. All right, so let's do some number lines. Number lines for extra detail. Maybe I'll get it in there and voice over the JD part. Throw them off. Number lines for extra detail. So we're going to do this for f prime, and we're going to do this for f double prime. I'm going to line them up. So I'm syncing them up. Critical values I'm going to mark off. 0, square root of 3, negative square root of 3. And then I'm gonna look down at the second derivative. So this was my second derivative. Let's actually get that guy and do a little bit more work with him. F double prime of x was this. And let's factor that. Hey, can you factor that really quick, please? I wanna factor that thing. Not pleasant. Not pleasant. That's kind of a factorization right there. Let's set this equal to 0. And let's figure out where that second derivative is equal to 0, because those are going to be our possible inflection points. Let me put a note here, and you might want to put this. To find possible inflection points. And there's going to be 3. If you can maybe even see that by looking at this. Low-hanging fruit, you get 6x equals 0, or this thing. And I'm definitely going with the way you did on that one, Sam. I'm not factoring it. I refuse.
It's not working.
It ain't. Like that. I'll stop. Make sure you're getting it and it's rolling for you. We should be getting x equals 0, and then x equals plus minus square root of 3 over 2. Which is like, could we get a calculator, friend, on that? What is the square root of 3 halves? Square root of 1.5. I just want to have it so I can approximate it.
1.22.
That's good. I can probably not do better than 1.2.
1.22.
Okay. If you insist, I'll try for that extra 100. There we go. Now it's right. Now we're doing rocket science. So on this F double prime graph, I'm going to mark these guys off. And I'm going to mark them off relative to these guys up here. So here's 0. Cool. And then this is like 1.732, if someone's keeping me on. This is negative 1.732. Just because I've done square root of 3 a lot in my life. Kind of one of those numbers I see often. And then, so that one down there's in more. So we've got like square root of 3 halves is right here, and then it's in here as well. So what I'm trying to do is actually make it less distance away from 0 than the previous 2 things up here. And let me mark those guys off. So let's do the first derivative info. And let's do it simply. I'm going to put f prime of x right here so we can look at it. F prime of x factored. We've already done it. I'm going with the SAM factorization. X squared minus 3. And then f double prime is that mofo right there. So 6x, 2x squared minus 3. Now I can do what I need to do easily. Let me stop while you get caught up. Because I'm going to test those signs of those derivatives in each of the regions in each of these things. Which sounds painful, but it's not. So to do, let's go here. Pick a number that's super negative. Negative 1,000,000 is in this region. I'm going to go for x is negative 1,000,000. Positive. What's this going to be when x is negative 1,000,000? Positive. So here f prime is positive. Isn't that easy? You don't have to get too crazy. See, I'm just guessing what it is. Now, inside here, this one's a little trickier, but we can do it. I have a number that's less than the square root of 3 in magnitude. So when I put it in here, what if I put a number that's less than the square root of 3 in here? What does this become? This is negative. So yeah, if the magnitude of this x is less than the square root of 3, then this is less than 3. And that makes this whole thing negative. What about this guy? Do I have to stress about this ever? No, that's always positive, right? So this is always positive. That's good. So in here, I've got a negative number, so f prime is negative. We kind of knew that because we knew there was a max there, but we're just validating that information. See how the first derivative test gave us that? And then in here, we can kind of, let's just keep hacking it here. So f prime is negative here, I can test that. And f prime is, what do you think it is here? Positive, look at the graph. There we go. Cool. All right, let's do this guy. Same way. If I'm super negative, x is very negative. Negative. What is this when x is very negative? Positive, because you square it first. So I have negative times a positive. Here, f double prime is less than 0 in that region. That means you're concave down. We kind of knew that, the way I drew the graph anyway. I was assuming that, but you see it, see that concave down. And then in here, so I've got another region here. What about in this region? So like x is negative 0.1. Think of a number in here. X is negative a tenth. Negative. What is this when x is like close to 0? Negative. See, when x is a very small number, this is a very small number, and this is negative. And when x is negative, this is negative. So in here, f double prime is positive. Now on this side, kind of the same thing. Inside here, I'm going to use x is a tenth. Positive, negative, f double prime is negative in this region. Last one, x is a big ass number. X is a freaking billion. Positive, positive. F double prime, positive. It's tedious, but it doesn't have to be that bad. Don't get hung up on the exact values. Worry about positive, negative. And I'm trying to like kind of show you how to do that in the same time. So now we're almost done. We've got 5 minutes. We're gonna put this shit together, make a beautiful graph for ourselves, and we're gonna improve upon this beast right here. So let's start pulling the information together. And let me do it the way I would do it if we hadn't done some work already. Let's say I gave you, this is like exam stuff, right? I give you this stuff right here and say, make a graph based on this information. So the first thing you do is you go to your first derivative. Luckily, I know that 0, 0 is on there, so I got an anchor point, but I see that I'm going up to the left side of -3, and I'm going down between negative square root of 3 and 0. And then here I keep going down, and this is positive square root of 3, and then I go up. That's first draft. Draft 1, make it sharp, make it crappy. Only get increasing, decreasing info. Then tweak it with this. And you can make it so freaking beautiful with this information here. So this one, what was this number? Oh shit, what was that, like 1.2?
1.22.
1.22. So let's put that on here. Let's put negative square root of 3 halves right there, and positive square root of 3 halves right there. That's 1.7, that's 1.2. Good enough. Look at what happens to the left side of negative square root of 3 over 2. I am concave down. I'm scooped down. So when I tweak this thing, it's concave down up till there. And then it becomes concave up between here and 0. So here, it kind of starts to scoop up like that. And get rid of my first draft. Concave down, see how pretty that is? So subtle. And then here, between these two values, I'm concave down. So I'm gonna make that a little bit better, and it's like that. It's concave down in there. And then finally, to the right of this value, it's all concave up, which makes sense with what else I know. And I got that graph. Isn't that pretty? Look how the little subtleties in there, so freaking cool. You get out your Desmos, you get your graphing calculator, you're gonna get a graph just like that. The last thing, and I'm too tired to do it, I can see you're too tired to hear it. But what we would do is find what is the value here, what is f of x here, the actual height. We would put it into the real, so in other words, what's f of square root of 3? It's plug it in there. And then here, this is f of negative square root of 3. We would compute those and get those on the graph. That's it. That's what you get to do on Friday. Yay. All right, friends, that'll be it. Welcome back. Oh, we will not meet the Friday of Halloween if you weren't here when I announced that. I'm not going to be here on Friday the 30th. You could be here. I'm not going to be here. You do you. No. Oh wait, is it Friday's the 31st? Oh shit. Man, I hope my friend made reservations. I'm not paying for the 30th. I can't leave then.